Okay, so we have been talking about polynomial functions for a while now. Now we're going to talk about another kind of function, rational functions. And here to get us started are some examples of rational functions. You'll notice right away that each one says y equals, and then you've got a fraction-looking expression on the other side of the equal sign. So rational functions are functions in the form of a ratio of polynomials. So the numerator and the denominator are both polynomials, although they might be the kind of polynomial that just consists of one term, or they might have more than one term. And when you look at the graphs, you might notice that the graphs are not necessarily all in one piece. They may consist of more than one piece separated, and so they don't look the same as the graphs of polynomial functions. We'll talk more in a little while about what they do look like and how you can tell what the graph of a rational function is going to be. But first, some sort of real-world examples of rational functions or situations that are described or modeled by rational functions. So I stole these out of some book or other, but this first example says the cost C in dollars of producing X tennis balls is C equals 150,000 plus 0.25X. So you can think of that as maybe it costs $150,000 to buy a tennis ball making machine, and then it costs 25 cents for the material for each individual tennis ball that you make with that machine. So if you're going to be making X number of tennis balls, it's going to cost you altogether 150,000 plus 0.25x dollars. Then the average cost per tennis ball would be if you take that total cost and divide it by the number of tennis balls you're making. So 150,000 plus 0.25x over x. If I take that function and I draw the graph, or I ask my graphing calculator or my graphing software to graph it for me, here's what it looks like. Now, really, the only part of the graph that really applies here is the part where the x coordinates are positive, because we can't be making a negative number of tennis balls. So really just focus on this part of the graph. Notice how it goes way up here, and it sort of flattens out over here. That's because if you're not making very many tennis balls, if you're only making a few, the average cost per tennis ball is going to be really, really high. But if you make lots and lots of tennis balls, then the average cost per tennis ball gets a lot lower. In particular, if we take this function and plug in 1,000 for x, what we get out is 150.25, which means that if we make 1,000 tennis balls, the average cost per tennis ball is $150.25. That's not really sustainable. You're not going to make much money if you have to spend $150.25 per tennis ball. And that's because that tennis ball making machine was awfully expensive. And if you only use it to make 1,000 tennis balls, and each one of those 1,000 tennis balls has to cover part of that cost of the tennis ball making machine, then each tennis ball's share is $150 plus the 25 cents for the materials. Now, if you make 10,000 tennis balls, then the average cost per tennis ball goes down to 15.25. If we plug in 100,000 for x, we get an average cost per tennis ball of $1.75. If x is 2,000 or $200,000 or 200,000 tennis balls, then the average cost per tennis ball goes down to $1. And if you were making 1,000,000 tennis balls, then the average cost per tennis ball would be just 40 cents. So the greater x is, the smaller the value of this rational function is. We'll come back to this example later on and talk more about what's going on here sort of in the long run. But first, another example. This one says the cost C in millions of dollars of removing P% of the industrial and municipal pollutants discharged into a river is C equals 255 times P divided by 100 minus P. Again, if I put this into my graphing software, ask it to draw the graph of this function, here's what it looks like. And again, the only part that really applies is the part where the number you plug in is a positive number. So the x-axis, that's really what you're plugging in for P, and the y-axis is what you're getting out for C. So if we plug in 15, we get out 45. That means that the cost of removing 15% of the pollutants is 45, and C is in millions of dollars, so $45 million. Plug in 50, and we get 255. So the cost of removing 50% of the pollutants would be $255 million. If we want to remove 80% of the pollutants, plug in 80 for P, we get 1,020. So that would be $1,020 million, or a little over $1 billion. What if we want to remove 95% of the pollutants? That's going to cost $4,845 million. Well, what if we want to remove 99.9% of the pollutants? If you plug in 99.9 for P, you get a whopping $254,745 million. And if you plug in 100, thinking you're going to remove 100% of the pollutants, completely all of the pollutants, well, then you get a division by zero error. The function's undefined, which means that according to that equation, you can't remove 100% of the pollutants. So according to the model, it would not be possible to remove 100% of the pollutants. And notice how the bigger a percentage you remove, the more expensive it gets, the higher the cost gets, and there's no limit to how high it gets. The graph just shoots way up there. Third example. The Game Commission introduces 40 elk into newly acquired state game lands. The population N of the herd is given by N equals 10 times the quantity 4 plus 2t over 1 plus 0.03t. And if you wanted, you could remove the parentheses and write it as 40 plus 20t over 1 plus 0.03t, where t is the time in years. So after t number of years have gone by, this formula is supposed to give you the population, the number of elk that there are going to be after that many years. Here's the graph of that function. So as we go forward in time, the elk population is increasing. It's getting bigger and bigger, but it looks like there's a limit to how big it can get. It looks like as we go off into the future, the elk population is going to be leveling off. It's not going to get up to 1,000. Instead, it's going to level off at, I don't know, will it go above 600? How high will it get? We'll come back to this. But notice that if you take this formula and plug in 5, you get 122, meaning that 5 years after those 40 elk are introduced into the game lands, the population has grown to 122 elk. In 10 years, the population has gotten up to 185. After 25 years, we have 309 elk. Plug in 50, you get 416. And if the model or equation continues to be accurate, it would predict that 200 years from now, the number of elk would reach 577. Now let's talk a little more about what's going on with rational functions in general. Here's just a rational function that we can play with that doesn't stand for anything. It's just y equals 2x minus 6 over x minus 4. And here's what the graph looks like. Notice it's in two pieces. When you look at the equation, you'll notice that we've got a denominator of x minus 4, and that if you plug in 4 for x, you'd have a 0 in the denominator and the function would be undefined. We'd have a division by 0 error. That's why there are no points on the graph with an x coordinate of 0. You've got points with x's less than 0, there's no points on the graph with an x coordinate of 4. There's points on the graph with x coordinates less than 4, and there's points on the graph with x coordinates greater than 4, but no points with an x coordinate of exactly 4. In fact, if we draw a vertical line where x equals 4, the graph of the function never quite touches that line, but it does get closer and closer to it. As we go up here or down here, the graph sort of straightens out and becomes more and more like that vertical line x equals 4. And so we say that line is an asymptote, a vertical asymptote for that graph. The word asymptote means a line that a curve approaches or gets closer and closer to or becomes more and more like. Also notice what happens as we go off to the right or to the left. The graph straightens out and gets closer and closer to or becomes more and more like this horizontal line here, the line y equals 2. So that's a horizontal asymptote for this graph. And so in general, when you have a rational function, you very often, not always, but often have a vertical asymptote, and you have very often, but not always, a horizontal asymptote. So how can you tell where those are going to be? Well, the vertical asymptote is where the denominator is 0. Here, the denominator would be 0 where x is 4, so the line x equals 4 is a vertical asymptote for that graph. The horizontal asymptote, well, there the rule is a little more complicated. You have to look at the degree of the numerator and of the denominator. And then depending on what those are, here's what that tells you about the horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then the line y equals 0, which is the x-axis, is a horizontal asymptote for the graph. When the degree of the numerator is the same as the degree of the denominator, then you look at the leading coefficients. Leading coefficient on top divided by the leading coefficient on the bottom. The line y equals that number is the horizontal asymptote. And that's what happened in this example. The numerator and denominator were both degree 1, same degree as each other. The leading coefficients were 2 on top over 1 on the bottom. So the line y equals 2 over 1, or just 2, was the horizontal asymptote. The third possibility is if the degree of the numerator is greater than the degree of the denominator, then the graph doesn't have a horizontal asymptote. Now, it might have a diagonal or slant or oblique asymptote, but it doesn't have a horizontal asymptote. So we'll look at some more examples in the next video.